Wood is what people build with. Stone if they can afford it. Brick if they can fire it. But wood is the default, the thing a builder reaches for first, and bamboo is what turns up when the wood has run out. That is the assumption almost everyone carries around without ever examining it. Then there is Hong Kong, a city with no shortage of money and no shortage of steel, where crews spent decades wrapping residential towers over 200 meters tall in a grass, lashed joint by hand, going up faster than a metal system could be trucked to the site. Industry estimates put roughly 4 out of 5 of the city's scaffolds in that category. Not a poor city, not a shortage of anything. And monsoon Asia was never short of timber either. That has to be said, plainly and early, because the rest of this falls apart without it. The forests running from southern China through mainland Southeast Asia and out into the islands held some of the best structural hardwood on the planet. Teak, ironwood dense enough to sink in water. Chinese carpenters raised the timber halls that have ridden out centuries of earthquakes on interlocking bracket sets cut so precisely they need no nails at all. And Japanese temple carpentry set a standard of jointing that structural engineers still take apart and study today. Nobody in this part of the world was using bamboo because they had never seen a good plank. So the claim has to stay narrow. For monumental building, for temples and palaces, and anything meant to outlive the people who paid for it, timber won across most of monsoon Asia, and it deserved to. For everything else, bamboo won. Everything else is a large category. The houses most people actually lived in: bridges, water systems, ladders, pipes, ducts, rafts, fences, granaries, fish traps, and the temporary structures that make permanent building possible in the first place. Bamboo won that category on a specific short list of properties, and getting that list right is the entire story. Start with what the material is, because almost nothing about it behaves like a tree. Bamboo is a grass, more than 1,000 species of it, spread across the tropics and the warm temperate zone, and the part that gets built with is the culm, the hollow stem, closed off at intervals by solid internal walls called nodes. A tree trunk is a solid cylinder that lays down a fresh ring of wood each year and thickens for as long as it lives. A culm does none of that. A shoot pushes out of the ground already at its final diameter, and it will never be 1 millimeter thicker than it is on the day it appears. What it does instead is extend, and it extends at a rate that looks like a misprint. The giant timber species put up their entire height inside a single shooting season of roughly 2 months, and the fastest shoots ever measured added more than a meter in 24 hours. Then the growing stops permanently. The culm spends the next few years hardening in place, and somewhere between the 3rd and the 5th year, it is ready to cut. The first time I read that a bamboo culm never gets thicker, I assumed I had misread the sentence. That harvest number is the first axis, and it's doing more work than any of the others, 3 to 5 years, against a 20 to 60 for structural timber, out of a rootstock that keeps sending up replacements without being replanted. A household with a stand of bamboo behind the house is not managing a forest. It is managing something much closer to a crop. The second axis is shape. A hollow tube is a genuinely efficient structural section because in bending, the stress concentrates at the outer surface and the material in the middle of a solid pole is mostly along for the ride. Bamboo puts its fibers where the load is, so it packed densest in the outer few millimeters of the wall and thinning towards the inside. The nodes work as diaphragms, which is why a culm resists being crushed flat, and why it will take a bend that would snap a stick of the same weight. This is not a design anyone arrived at. It is a plant solving a wind problem, which happens to be the same problem a builder has. Jules Janssen spent a career at Eindhoven, turning that into numbers a structural engineer could actually use, and his measurements are still the backbone of a lot of what gets designed today. Here's where a popular claim needs correcting, because it circulates constantly and it is wrong. Bamboo is not stronger than steel. It never was. Pulled along the grain, culms test somewhere between about 115 and 370 megapascals depending on species, on age, and on where along the culm the sample was taken, while mild steel sits in the range of 250 to 415. Steel wins on the raw number, and it is not close on stiffness. The honest version of the claim is about weight. Bamboo achieves a large fraction of steel's tensile strength at a small fraction of steel's density, which is a real and useful property and is not the same sentence at all. The comparison worth making is the one nobody makes. Against wood, bamboo in tension is in a different league, with pine and oak landing somewhere around 50 to 100 megapascals. Per kilogram carried up a hill on one shoulder, the grass beats the timber. That advantage runs a long way further back than any building. There is a serious argument in Paleolithic archaeology that this plant explains a hole in the stone tool record across half of Asia. Against that, the weaknesses are real, and none of them are small. A column splits along its length with very little encouragement, which makes every bolt hole a liability and turns connections into the permanent engineering headache of the material. The variability is enormous, so two poles from the same stand can test far apart, wildly far apart, and it rots. Bamboo carries no natural toxins and a lot of starch, which is an open invitation to powder post beetles. And because the wall is thin, a small amount of decay removes a large fraction of the structural capacity. Walter Lisa, who spent decades in Hamburg on the anatomy of the plant and became the standard reference on how it fails, laid out what the traditional treatments do and do not achieve. Soaking cut culms in a river or a pond for a few weeks leaches out starch and sugars and measurably cuts the risk of beetle attack, though it does very little against termites or fungal decay. Curing over a smoky hearth kills the insects living inside and lays a thin protective layer on the outside at the cost of some heat damage to the fibers. Cutting at the right season when starch levels are low helps at the margins. None of it makes bamboo permanent. Nobody using it thought it did. Japan turned that smoke treatment into something slower and stranger. Traditional thatched farmhouses were framed with bamboo in the roof structure, and underneath sat an open sunken hearth that burned more or less continuously through the cold months. Decade after decade, the smoke rising into the roof space dried and darkened the culms above it. The result is called sosudak, soot bamboo, and it is commonly said to take a century or two to happen properly. When such a house is finally dismantled, that blackened roof bamboo is not firewood. It is salvaged and sold on, and craftsmen in Nara turn it into tea scoops and whisks, with the pale stripe where a lashing cord sat left, visible as proof of where it came from. A preservation process running on the slowest possible schedule as a side effect of cooking dinner. Nobody designed that. Picture the actual job. Somewhere in lowland Southeast Asia at the end of a wet season, a household needs a house, or needs most of one again. Two people walk into the stand behind the settlement with a heavy knife and cut what they need, selecting for a culm that has been standing 4 years. Because the neighbors can all tell a 4-year culm from a 2-year one by color and by the sound it makes when struck. There is no saw pit, no team of oxen to drag anything, no seasoning shed, no years of waiting for planks to dry, no specialist who has to be paid. The culms are carried on shoulders, split lengthwise with the same knife, flattened into wall panels by scoring and unrolling them, and lashed with cord cut from the same stand. The frame is up in days, sometimes 2. The house will need serious attention within a decade, and everyone involved knows that on the day it goes up. That last sentence is the part that gets missed. The building was never intended to be a permanent object. It was intended to be a renewable one. The evidence for how far that idea scales is not a house, though. It is a waterworks. Before that, an awkward problem worth admitting. Almost none of this early history survives in the ground. Bamboo decays completely in tropical soil, and stone does not. So the archaeological record of monsoon Asia systematically over-reports one and erases the other. Whole technologies could have run for 100,000 years and left nothing but an absence, a hole in the record. That absence produced one of the more interesting arguments in Paleolithic archaeology. Hallam Movius noticed in the 1940s that the classic Acheulean hand axe, everywhere in Africa, Europe, and Western Asia, thins out and mostly vanishes east of a line drawn across the northern India. East of it, stone toolkits look simpler, cruder even. For decades, that pattern was read as evidence that early populations in East and Southeast Asia were somehow behind. In 1989, Jeffrey Pope published a different reading, that the Eastern Zone maps onto the natural range of bamboo, and that people there were not failing to make sophisticated cutting tools, but making them out of something that does not fossilize. A split column takes a working edge in seconds and can be resharpened endlessly. It is a genuinely attractive idea, and it is contested. Experimental work has tested how bamboo tools perform in butchery and how their cut marks differ from stone ones, with mixed results, and hand axes have since turned up east of the line anyway, notably in the Bose Basin in southern China. Between the two readings, I find myself closer to the critics for one specific reason. The hypothesis explains why we would not find the tools, but that is not the same as explaining the stone pattern that started the argument, and a hypothesis that only accounts for missing evidence is hard to test. What I would say with confidence is narrower. The material's invisibility is real, it is severe, and any picture of ancient technology in this region built only from what survives is going to be wrong in a predictable direction. Now the waterworks. Around 256 BC, on the Min River in what is now Sichuan, an official named Li Bing began a project to stop the annual flooding of the Chengdu Plain and irrigate it at the same time, without building a dam across the river. The system divides the flow with an artificial island, sheds excess water and sediment over a spillway, and feeds the plain through a channel cut through a mountain spur. Dujiangyan is still in operation, not as a monument. It irrigates a large agricultural region today, more than 2,200 years after it was begun, and it is a UNESCO World Heritage Site. The parts that shaped the water were made of bamboo, long woven bamboo baskets filled with river cobbles, stacked to form the dividing works and the spillway, held in position by wooden tripods. Not one of those baskets was expected to last. Not one did. The whole system ran on an annual maintenance cycle, dredging the channels each winter and weaving fresh baskets to replace the ones the river had chewed through. Think about what that means as an engineering decision. A structure that has to survive a mountain river in flood, built deliberately out of the least durable material available and outlasting almost every masonry dam ever built. Deliberately. It works because the failure is designed to be cheap. A stone barrage that cracks is a disaster requiring a generation and a treasury to repair. A basket that bursts is a morning's work for people who already know how to weave. The system's durability lives in the maintenance cycle and in the skills of the people nearby, not in the material. The same logic held for crossings. Suspension bridges strung on cables of twisted bamboo carried traffic over the gorges of western China for centuries, in country where a stone arch was impossible and a boat was worse, with the cables spun on site from thousands of split strips and stretched between timber towers set into the rock on either bank. The best known of them stands at Dujiangyan itself, rebuilt in 1803 at the urging of a local teacher named He Xiande and his wife, with a plank deck and bamboo handrails, cables as thick as a bowl, spun from split culms, replaced on a schedule. The bridge is still there and people still walk across it, though the bamboo cabling was swapped for steel in the 20th century and the timber piers for concrete. So picture the other scene. It is winter, the river is low, the channel has been temporarily blocked off, and hundreds of people are working in the dry bed. Silt goes out by the basket load, thousands of them. On the bank, others are weaving cages 3 or 4 meters long out of split bamboo, which are then dragged into position and packed with stone by hand. Nobody in that crowd is building something permanent. They are doing this year's version of a job that was also done last year and that their grandparents did And that would be done again the following winter for the next 22 centuries, which brings the whole thing to its point. Bamboo never won on durability and it never won on absolute strength. It won on time. Time to grow a replacement, time to cut and carry it, time to put it up, and time before the next repair was needed anyway. In a climate that takes buildings apart on a schedule, with a typhoon season, a monsoon, termites working year-round, and earthquakes on top, permanence was simply the wrong target. Anything built to last 1,000 years there was going to be destroyed long before the 1,000 years were up. The rational strategy is not the strongest material. It is the material that can be replaced faster than the climate destroys it, and by the people who live in the building rather than by specialists who have to be summoned and paid. Modern building went the other way completely, and it is worth seeing what that cost. A house made to last a century is a house nobody in it knows how to repair. It also helps to notice who never had the choice. Europe north of the Mediterranean has no native bamboo of any building size, and never did. Neither does most of the Near East. It simply does not grow there. The entire tradition of European construction, the stone and the seasoned oak and the multi-generation cathedral developed in places where the fast-growing hollow tube simply was not an option in the landscape, and where the climate was not tearing structures apart at anything like the same rate. That comparison usually gets told as a story about ambition, with permanent stone standing in for civilization and a light frame standing in for something less. It is a story about botany and rainfall, nothing more. Two regions optimized for different failure rates using what grew there. The end of this is happening right now, and it is not sentimental. In March 2025, Hong Kong's Development Bureau issued a memo requiring metal scaffolding on public works tenders with bamboo permitted only by exception and with written justification. The reasons cited were inconsistent mechanical properties, deterioration over time, and combustibility, which is a precise list of the material's real weaknesses rather than a vague appeal to modernization. Official figures quoted at the time recorded 23 deaths in bamboo scaffold accidents since 2018. The safety argument is not one I would want to stand against. And bamboo has not gone anywhere in the private sector, for exactly the reasons it never went anywhere in the first place. A bamboo pole costs a small fraction of the equivalent metal component. Crews put it up and take it down faster, in tighter spaces, around awkward geometry, carrying the material up by hand. Worth watching how it is actually assembled, if the chance comes. There are no bolts and no clamps, none. Every joint is a lashing, tied by hand in seconds by someone standing on the frame they are building, and the whole structure is deliberately a little loose, so that it moves with wind and load instead of resisting it rigidly. The knowledge sits entirely in the hands of the crew, which is also the reason the trade is dying. It takes years to learn, and fewer people each year are prepared to learn it. The axes have not changed in 2,000 years. The weighting has. Meanwhile, the material is being formally standardized. The International Structural Design Standard for Round Bamboo, revised in 2021, gives engineers a proper design method for the first time, and its scope is honest about the limits. 1- and 2-story buildings, up to 7 meters with scaffolding explicitly excluded and bamboo reinforced concrete dropped from the previous edition. Architects working at the top of the field, including Vo Trong Nghia in Vietnam, have built large public structures from tens of thousands of treated poles. What they are doing is the traditional calculation with better preservation chemistry and better joints. There is a stand of bamboo somewhere in southern China that will put up a new culm this spring at its full and final diameter and reach 30 meters before summer. In 4 years, someone can cut it. The stand will not notice.